For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. Figure 1. PA, E versus SNR, N or M for uncoded binary PM. Figure 2. PB, E versus EB/N0 for uncoded MXM, QAM. Table A, values of certain small factors alpha in dB. livexamhelper.com. Table B, parameters of certain Readmuller, RM, codes. livexamhelper.com. Table 1, rate 1/2 binary linear convolutional codes. Table 2, rate 1/3 binary linear convolutional codes. livexamhelper.com. Table 3, rate 1/4 binary linear convolutional codes. Problem 1. In this problem we consider a convolutional code C over the quaternary field F4. The elements of F4 may be denoted as 0, 0, 0, 1, 10, 11 additive representation, or as 0, 1, a 2 multiplicative representation, where is a primitive element of F4 and a root of x2 plus x plus 1. You might wish to jot down the addition and multiplication tables of F4. The convolutional code C is generated by the encoder shown below. livexamhelper.com. The input UK at time k is an element of F4, and the delay element, denoted by D, stores the previous input UK underscore. There are two F4 outputs at each time k, whose equations are Y1k equals UK plus UK1. Y2k equals UK plus alpha2 UK1. A. Show that the convolutional code C is linear over F4. B. Let U, D, M, D, and Y2, D be the D transforms of the sequences UK, THENK, and Y2k respectively. Give expressions for E, D, and Y2, D in terms of U, D. C. Specify the number of states in this encoder. Draw a single section of a trellis diagram for C, labeling each branch with a quaternary 2-tuple, YR, Y2k, E, F4, 2. D. Show that this encoder for C is non-catastrophic. livexamhelper.com. E. Find the minimum Hamming distance free, C, and the average number of nearest neighbors CMIN, C, per unit time. Now define the binary image of C as the binary convolutional code C obtained by mapping the outputs YIKEF4 into the additive representation 0, 0, 0, 1, 10, 11, where each representative is a pair of elements of F2. F. Repeat parts A, E for C, replacing F4 by F2 where appropriate. For part B, map UKEF4 to its binary image. F. Repeat parts A, E for C0, replacing F4 by F2 where appropriate. For part B, map K2F4 to its binary image. G. Compute the nominal spectral efficiency P, C, and the nominal coding gain TIC, C, and estimate the effective coding gain REF, C, using our usual rule of thumb. Compare the performance of C to that of the best rate 1/n binary linear convolutional code with the same spectral efficiency and number of states, see tables above. Now define another binary convolutional code C as the code obtained by mapping the outputs KIK-EF4 into the code words 000, 011, 101, 110 in the 3A22 binary SPC code, where each representative is now a 3-tuple of elements of F2. H. Repeat parts A, E for C, replacing F4 by F2 where appropriate. For part liveexamhelper.com. B. Map UKEF4 to its binary image. I. Compute P, C, and 7C, C, and estimate IF, C. Compare the performance of C to that of the best rate 1/n binary linear convolutional code with the same spectral efficiency and number of states. See tables above. Problem 2. In this problem we consider graphical representations and decoding of the 3216-8 binary Reed-Muller code RM25. A. Show that there is a partition of the 32 symbols of this code into 4 8 tuples such that the projection of RM25 onto any 8 tuple is the 872 binary SPC code, and the subcode corresponding to each 8 tuple is the 818 binary repetition code. Moreover, the 8 tuples may be paired such that the projection onto each resulting 16 tuple is the 1611 4 extended Hamming code, and the subcode corresponding to each resulting 16th tuple is the 1658 biorthogonal code. B. Using part A, show that there is a normal realization of RM25, whose graph is as. liveexamhelper.com. Tip: to find the constraint code dimensions, you may use the fact, not proved in 6.451, that the constraint codes in a cycle-free representation of a self-dual code are self-dual. C. Using part B, give a high-level description of an efficient algorithm for maximum likelihood decoding of RIVI, TUG5, on an arbitrary memoryless channel. D. Compare the performance, probability of error, and complexity, number of arithmetic operations, roughly, of the algorithm of part C to that of the Viterbi algorithm applied to an efficient trellis realization of RIVI, 2-5. Hint: start by finding a trellis-oriented generator matrix for RIVI, 2-5, and then find an efficient sectionalization. liveexamhelper.com. Problem 3. For each of the propositions below, state whether the proposition is true or false, and give a brief proof. If a proposition is false, the proof will usually be a counterexample. Full credit will not be given for correct answers without an adequate explanation. A. The Euclidean image of an NKD binary linear block code is an orthogonal signal set if and only if k equals log 2 it and d equals n/2. B. Every element 0EF32 is the root of a binary polynomial f, x, EF2, x, of degree less than or equal to 5. C. If codewords in an NKD binary linear block code with d even are transmitted equiprobably over an AWGN channel using a standard 2-PAM map and are optimally detected, then the minimum squared distance to any decision boundary is twice the minimum squared distance that is achieved if binary hard decisions are made first on each symbol and then the resulting binary received word is optimally decoded. D. Capacity approaching codes must have trellis complexity parameters that become arbitrarily large as the Shannon limit is approached arbitrarily closely. liveexamhelper.com. A. If the points x in a lattice A are transmitted with unequal probabilities, p, x, xea, over an AWGN channel and optimally detected, then PR, e, p.1 Kearney, a, v, d, in a, /for u2, where d2.d, a, is the minimum square distance between points in A, and km1n, a, is the average number of nearest neighbors to each transmitted point. liveexamhelper.com. Solution 1. A. Show that the convolutional code C is linear over F4. If y1k, y2k, euro C and y11k, y12k, euro C are the output sequences corresponding to the 2k input sequences, uk, and u respectively, then the input sequence, uk plus u, generates kk the output sequence, y1k, y11k, y2k plus y12k.